The midterm test and final exam will be in person. The labs will be in person and online as well. So basically the TA will be in the lab. If you have questions, you can come to the lab and see him. At the same time, he has his laptop open with Zoom as well, so that he can help you. Office hours, again, will be in person and online as well. Now for the lectures, I'm asking you to complete a survey to help me understand what would be best for the class. All right, so if you go to at the bottom of the page, you and there are four options, A, B, C, and D. Please choose one of the four options and ignore the last option. The last option I had to do it because this is basically a multiple choice question in e-class, and I must have a correct answer, right? And then for the other four options, each option gets 25%, but this is not about your grade, it's about a survey. Okay, so I will add together the marks, and from the marks I can infer how many people choose each option. Okay. So right now we have 31 students in the class. Why don't we take about 3 minutes to complete this survey for me, please? Okay. All right, so let me see how many people have completed. So please take about 3 minutes to complete the survey for me, please. That would help a lot. So we have about 40 students in the class. Right now there are 31 present. So if I can get your preferences today, that would be great. Okay, so please take about 3 minutes to complete the survey. There's a question on the chat window. Do we have a quiz today? Yes, we'll have a quiz today. Okay. All right, so I'm waiting for another 2 minutes. And please ignore the correct answer feedback at the end, like I said, yeah. So everything we cover from the beginning up until the last lecture will be on the quiz. Okay, so, oh no, the quiz will be online. The quiz will be during the lecture time here. So during the lecture time here, we have a quiz on e-class, just like any other quizzes or tests you did on e-class in previous classes. Okay, so the quiz will be just like a multiple choice question quiz on e-class, just like what you did in the past in other courses. No, we didn't have a quiz last lecture. This is the first quiz of the course. Okay, so let's see. Okay. All right. So okay. So thank you everyone for completing the quiz. Do you have any? Do you have any? Anyone still need time to complete the survey? Anyone? If so, please raise your hand and I'll wait for another minute or so. Okay. All right. All right. So I think no one need more time. Okay. So that's good. All right. So now for the quiz, basically the quiz is very similar to what you just did now, the survey. All right. Later around 3:15, we'll have the quiz. So I just want you to warm up a bit. The quiz is very similar to what you did now with the survey, except that it has more questions and then yet you have more questions, more time, exactly. But the format is similar. Okay. All right. And there will be a password as well. And I will type the password in the chat window. All right. Okay. So thank you everyone for completing the survey. I will check the numbers and then I'll get back to you with a final decision about how we will conduct lectures online or in person. All right. But again, just to remind again, the test, the midterm test and the final exam will be in person. The labs will be in person and online. Office hours, again, in person and online. The lecture will be decided after I tabulate the results from the survey. Okay. All right. Thank you, everyone, for completing the survey. Now, let's begin the lecture. So I will start with signals and signal propagation first. Okay. So the first part is signal. It's basically a very quick review of what you learned in 3213. Okay. So let me show here term signal. Okay. Right. Page 15. Okay. So this is what you learn from 3213. So basically, a signal is represented by a either a sine wave like this. This is analog signal, or this one, it could be digital signal, right? And if you present a signal by a sine wave, then there are three parameters that we have to take into account: the amplitude, which is the maximum strength of the signal, and it's measured by volts, right? And the frequency. The frequency is the rate of the change of signals. And the unit to measure the frequency is hertz. Basically, 1 hertz is 1 cycle per second, right? If you have, let's say, 1 kilohertz, all right? If it's 1 kilohertz, then how many cycles do you have per second? 1 kilohertz, how many cycles per second? Anyone? 1 kilohertz.
1,000.
1,000, right. 1 kilohertz is 1,000 cycles per second, exactly. 1 megahertz. 1 megahertz.
10 to the power of 6.
All right, 10 to the power of 6, which is 1 million, exactly, 1 million cycles per second, all right, because we use the hertz and kilohertz and megahertz a lot. That's why I have to help you record this information. And the phase, right, relative position in time of a signal, okay? So there are three parameters. We have to remember this: amplitude, frequency, and phase, okay? All right, so next, so these are the example of different kind of sine waves, right? So you can see they change depending on, so this is a change from here to here is an amplitude, right? From here to here, it changed in terms of frequency, and from here to here, the first one and the fourth one here, they represent the change in phases, all right? So I'm sure that you've learned all of this in 3213. And then frequency and peak amplitude are most important. No, phase is also important as well. If we use, we convert digital data to analog, all right? So you analog signal, and we'll see later. Okay, so this is a very quick review about signals, all right? Represent signal by sine waves, okay? Okay, so you can represent any signal using sine waves, right? And what we do is we call a Fourier transformation. Given any signal, you can decompose it into a set of sine waves. And when you add those sine waves together, you get an approximation of the signal. So for example, this represents a square signal, all right? The last one here, this one here is a square signal, right? And you can approximate the square signal here using two sine waves, this one and this one. If you add these two together, you get an approximation of a square signal, all right? So this is called a Fourier transformation. You convert a square signal into a set of sine waves, okay? All right, so that's the signal. Now, if you have digital data, so for example, you type a text message on your cell phone, you type an email on your cell phone, that will be stored as digital data. But now if you want to send the text message, the email through the network, through air, the signal in the air, in the medium will be analog signal, basically a set of sine waves, all right? So how do we convert digital data into analog signals, okay, into sine waves, right, into sine waves? Okay, that should be the next set of slides as a review for you. Okay, let's get this down and then. All right, just to make sure that you have seen this before, right? Everyone, you've seen this before, right? Okay. So not this one. Modulation. Okay. Now page 7. All right. Okay, so if you have digital data and you want to convert digital data to analog signals, right, into sine waves, then there are three major approaches, right? The first one is called amplitude shift keying, ASK, right? Amplitude shift keying. So in this case, for example, you use an amplitude of 0 volt to represent bit 0. And you use an amplitude of, let's say, 1 volt to represent a digit 1, right? So 0 digit would have a different voltage, and digit 1 would have a different voltage, right? So that's why we have the term amplitude shift keying, right? So that's how you use different amplitudes to represent 0 and 1. The second scheme is called frequency shift keying, all right? Frequency shift keying. So in this scheme, digit 0, bit 0 and bit 1, they have different frequencies. So you can see, let's say with bit 0, we represent it using 1 hertz, right? Let's assume this is 1 second. We have 1 cycle per time unit for digit 0, 1 cycle per time unit for bit 0. And with bit 1, we would have 2 cycle, right, to represent bit 1. 2 cycle to represent bit 1, all right? So by using 2 different frequencies, you can represent 0 and 1, okay? Another type of conversion is called phase shift keying, right? So with phase shift keying, we have 2 different phases for 0 and 1. So you can see with 0, it will go down, right? And then up to the peak and then down, right? So it will start from the middle, go down and up and down. Again, for 0, down, up and down. For 1, it's the reverse. You start from here in the middle, you go up and down and then up, right? up, down, and up. So that should be bit 1. Okay, so we use two different phases to represent 0 and 1. Okay, any question about this? All right, so so you can see here that we in these very simple examples, we use two amplitudes or two frequencies or two phases to represent 0 and 1. All right. In practice, you can use different more than two different values to represent more than one bit, right? So in this example here, one amplitude represents 0, one amplitude represents 1. One frequency represents 0, one frequency represents 1, right? But to be more efficient, you can use, for example, 4 phases, right? 4 phases. That means you can use the same amplitude A, the same frequency FC, but you use 4 different phases. And if you have 4 different phases, then each phase can represent 2 binary digits, right? 2 binary digits. So let's say pi over 4 represents 1, 1, 3 pi over 4 represents 1, 0, and so on, right? So this, in this case, it's called, it's not called binary PSK anymore. It's called quadrature PSK. Quadrature means 4, right? And each element, each signal now represents 2 bits instead of 1. So it's more efficient, all right? And that's how you can encode more data within a single signal. So it could be more efficient and you can have high speed data, right? And even going further, you can have a combination of phase shift keying with amplitude shift keying. So in this case, you can see here, it will have 12 angles, 12 phases, all right, 12 phases, okay? And 4 of the 12 phases, so let's say this phase here can have 2 amplitudes, all right? This phase here can have 2 amplitudes. This phase can have 2 amplitudes, and this one have 2 amplitudes as well. So in total, you have 16 combinations, right? 12 angles. And then 4 of these angles would have 2 amplitudes. So in total, you have 16 combinations. And with 16 combinations, each signal can represent 4 bits, right? So each signal now can represent 4 bits, all right? So you can even have even more, more data encoded, all right? Now, the problem, I mean, this is good because now you can encode more data with only one signal, right? So it's very efficient. The problem with this is if you are not careful, the design is not good, the transmitter is not good, the receiver is not good, the medium is not good, then for every signal that is destroyed, right? Or every signal that is lost, you lose 4 bits instead of 1, right? You lose 4 bits instead of 1, okay? So that means in this case, you have higher efficiency. You can send more data within one signal, but the error rate is higher than if you use only, let's say, 2 amplitudes or 2 frequencies, only 2 phases, all right? So that's the trade-off, higher efficiency, but you can also have high error rate as well, because every time a signal is destroyed, you lose 4 bits instead of 1, okay? All right, any other question about this? So I'm sure that you've seen this in 3213, right? Okay, so now that's a review. Now we go into signal propagation. Okay, so let me go into signal propagations. All right, so I'm going through signal propagation, but quickly, because a lot of these materials were taught in, I guess, part of it in 3213 and part of it in your physics courses as well. Okay, and please feel free to ask questions by typing in the chat window or raise your hand, right? So, but I expect that you have already learned this material through 3213 and your physics classes in high school and university. So let me, oops, sorry, I think I should put here 5431 as well. Okay. All right, so now we'll talk about signal propagation for wireless communications, right? So this is only for wireless. So assume we have a sender here in the middle here, and then a receiver, okay? A receiver here at this, the tip of the arrow. So there are three types of transmission ranges that we need to remember. First is transmission range, right? So whoever or whichever devices that are within this transmission range, all right? If it has a compatible antenna as the sender, it can receive messages from the sender and it can decrypt the message, right? Assume the message is encrypted, for example. It can decrypt the message. Basically, it can see clearly the signals, and then it can convert that in from analog signal to digital data with low error rate, right? So low error rate means there may be some errors, but the errors can be recovered, can be fixed, and then the message can be read, right? So that's called transmission range. It makes it's clear. Now, the second range is larger than the transmission range, is the detection range. So basically, the detection range will start from here, the sender, up to this boundary, right? So between the boundary of the transmission range to detection range, a receiver can hear the signal from the sender, but the signal may be too weak for the receiver to decrypt in order to get the message, all right? So basically, the receiver knows that the sender is sending something, but it cannot make out what the message is, all right? So what it means is it can detect the signal, but communication is not possible because the receiver cannot recover the message from the signal. All right, so it's imagine as if you were talking to someone standing a bit further from you, and that person was screaming, and you had, what are you saying, right? And that the person keeps screaming, but you cannot hear very clearly. So that's called detection range. All right, so in that case, in order to get the message, the receiver has to move a bit closer to the sender, move to the boundary of the transmission range or even closer, okay, to get the message. And then there's even a larger range, which is called interference range. So in this range outside here, a receiver cannot detect any signal from the sender. But because the signal is too weak, right? The signal is too weak, but at the same time, there is some signal there, and the signal will add to the noise, to the background noise that the receiver receives. So that means the receiver doesn't know that there's a signal from the sender because it's too weak, but the signal itself will add to the noise at the receiver, right? Okay, any question here? All right, so now, signal propagation in a free space is similar to propagation of light, right? It's in a straight line. And this is very important. The receiving power is proportional to 1 over d squared in vacuum, all right? In vacuum first. And d is the distance between the sender and the receiver, okay? And this value is reduced much more in a real environment. Okay, it must reduce much more in a real environment because of other noise, other influence I will see later. Now you can see here the reduction is d squared. So that means every time a receiver step away from the sender by one distant unit, the receiving power is reduced by the square of this. I mean, if it's twice further from the receiver, it's reduced by 4. 3 times, that would be by 9, right? 4 times would be by 16. So you see that the longer and longer the distance, the much more weaker and weaker the signal is. Okay. All right. So next, in addition to the distance itself, because as signal moves through a medium, even without any obstacle in vacuum, the signal becomes weaker and weaker. Now, on top of this, we have these problems. All right, so the first one is fading. All right, we'll see fading later in another slide. But what it means is the signal becomes weaker and weaker as it moves through the medium. Okay. The next factor is called shadowing or blocking. So basically, a signal is blocked by a wall, right? So if you have Wi-Fi using infrared technology, so the infrared technology cannot go through a wall. So it has to be limited in the room. But with other Wi-Fi technology, it can go through a wall. That is not too thick, right? Because the thickness of the wall also impacts the propagation of the signals, right? Okay, so that is shadowing or blocking. The next factor is reflection. Okay, so basically, just like light, the signal hits a surface, so it reflects. Okay, and we'll see later reflection will create problems with wireless communication. Another factor is refraction, right? So the refraction, I'm pretty sure that you learned this in physics courses in the past. When a light goes from air to water, the light is bent, right? The ray of light is bent. The same with another signal. The same, it will be bent as it goes through a medium with a different density. Another impact is called scattering. So in this case, a signal or the light hits an object, and then it will be scattered by the object, and it will have many other signal scattering from the object. Okay? And another influence is diffraction. So diffraction is a kind of scattering as well, but in this case, it doesn't hit an object in the middle of the object. It hits the edge, right? The edge, let's say this is the edge of a mountain, right? Or if you have a building, for example, it may hit the corner of the building, the edge, let's say here, or this wall here, it can hit the edge here. That's called diffraction, all right? Scattering is different from diffraction because of the way the light is scattered or the signal is scattered. Basically, both have the scattering effects, but to model them, you have to use different models because this one hits an object. This one hits the edge of an object, right? Okay, so next, so now, so in this course, we are only concerned with line of sight propagation, okay? But we'll talk a bit quickly about ground wave propagation and skywave propagation, okay? Now, ground wave propagation happens with frequencies less than 2 megahertz. Okay, we talked about hertz before, right? 1 hertz is 1 cycle per second. 2 megahertz means 2 million cycles per second. Skywave is between 2 and 30, and line of sight is about 30 megahertz. Okay. Now, from your physics classes, if I had a very long distance between 2 antennas, right, or between the sender and the receiver, I have very long distance between the sender and the receiver. Which type of frequency is better, higher frequency or lower frequency? If I have very long distance, higher frequency or lower frequency is better? Okay. All right, anyone? Yes, it has to be lower. All right. It has to be lower frequencies. Okay. So that because if you have very high frequencies, remember we talked about before, if you have very high frequency and you travel long distance, the signal will become weaker and weaker, right? And if you lose one signal, you lose more data, right? You lose more data. So that's why you need lower frequency if you have long distance. Okay, so keep that in mind. If you have very long distances, you need lower frequencies. All right. Okay. So that's one of the basic principles of wireless communication. All right. So ground wave. So basically, ground wave propagation is follow the curve of the Earth. All right. Follow the curve of the Earth here. Okay. And it's usually about less than it follows the contour of the Earth. It can propagate very far distances, and the frequency can be up to 2 megahertz, like as before, because the distances are very far. If we use high frequencies, the quality of the signal will be very bad. You lose a lot of data. And examples of ground wave propagation is AM radio, right? So you have radio station and they use AM frequencies. That would be a type of ground wave propagation. And we can have submarine communication as well. Again, underwater, because of the density of the water, you need to have very long wave as well in order to penetrate the density of the water. Okay. All right, sky wave propagation. So this one is usually used in satellite communication, right? So in this, so let me go back here. So you can see here the signals will be reflected from the ionized layer of the atmosphere back down to Earth. Okay. This is the ionosphere, right? And it's even though we say it's reflected, it's not really a reflection. We will talk about this later. But for now, you can think of it as a reflection, but it's not really a reflection because this is not a hard surface. It's just a layer of air here. And then it will go to the Earth. Here we have a reflection here from the surface of the Earth, go back up to the atmosphere here, and then it will be refracted, not reflected, back to Earth, and it goes through many cycles like this until it reaches the receiver. Okay. So the signal can travel a number of hops back and forth between the ionosphere and the Earth's surface. And as we said before, the reflection effect caused by refraction and not really by reflection. We'll see later when I talk about line of sight propagation. And the examples of skywave propagation is international broadcasts. For example, we tune in the radio, let's say from BBC in the UK, for example, because it's too far away, right? That's why we have international broadcasts here, international broadcasts. It's so far away, the signal have to travel a long distance and travel back and forth between the ionosphere and the Earth's surface to get to the receiver. It can be amateur radio or international broadcast, let's say from BBC in the UK, for example, to reach Canada. All right, so now any question here? Okay, so now we go to line of sight propagation, and this is what we're interested in, all right, what we study in this course. So for line of sight propagation, first, the distance between the sender and the receiver has to be shorter than compared with ground wave or sky wave propagation, right? Because we want a straight line of propagation here, so it has to be close. And because they are close, so we can use higher frequency, right? About 30 megahertz. All right, so example of these of line of sight propagation include mobile phone systems, right? The cellular network we're using, satellite systems, or cordless phone you use at home, all right? And the transmitting and the receiving antenna must be within line of sight. That's just like what we said here, must be within line of sight here, right? So because with satellite communication, if a signal is about 30 megahertz, it will not be reflected by the ionosphere, okay? That's why it requires line of sight communication. And then with ground communication, the antennas have to be within effective line of sight because of refraction. So we'll see in the next one. And what is refraction here? The refraction is the bending of microwaves by the atmosphere. Okay. So if we go to the next slide. Now first, as a signal goes through different media, remember refraction, the light will be bent, right? The light will be bent. And the bending depends on the density of the medium. So basically the velocity of an electromagnetic wave is a function of the density of the medium. And that's, I'm sure that you learned this in your physics classes, right? The denser the medium, the velocity is lower, right? And when the wave changes the medium, the speed changes and the wave bends at the boundary between the medium. Okay, if we go to this, diagram here, you can see this is the antenna, and this is where the sender transmits a signal, right? Now, this is the optical horizon. Optical means if you have a vacuum, right? Vacuum, there's no air, no whatsoever. The signal will travel in a straight line like this, okay? In a vacuum, it will travel in a straight line like this. Now, but remember the Earth atmosphere from the surface to up here, the density of the air changes depending on the altitude of the signal, right? What it means is, you can imagine as the density of the air changes from here to here. That's why it has a little bit of bending. And then the density of the air from here to here, they are different. That's why there's a bit bending, just like when we saw the previous diagram of a light bent at the surface of water. So when we go at different heights, we have different air density. And you can imagine a different air density represent a different medium with different density. That's why the wave of the signal keeps bending at not every, but as it moves through different altitudes, right? So that's why it goes this way. It doesn't go as a straight line. So the straight line is in a vacuum, but we have air, and air has different densities at different heights. So that's why the signal will be bent, right? Signal will be bent from here to here, okay? All right, so so there's a question in the chat room with what is D in this diagram. Okay, so now you understand why we have this bending, right? Before we go into that, why we have this bending here. Okay, the bending here is because of the air, and the atmosphere has different density at different heights. And remember refraction, when a light goes through different mediums, it will be bent. The same thing for this signal here. It will go through different mediums, different densities. That's why it's bent. Okay. Now we try to calculate the distance of a signal. If we use an antenna of height h, all right. If you have an antenna of height h, so it's here, all right? Then the distance that a signal can travel in vacuum is from here to here, okay? So this point here, okay, so let me use the pen. All right, so this point here, okay? So the distance from here to here is D, all right? If assuming vacuum, all right, assuming a vacuum. Now, because of, if we assume a real environment like the Earth here, you can see that the bending here, right, means that the signal can travel a bit further, okay? So that means now it can be around here, okay? So even up to this point here, okay? So now D would be this distance from here up to here. This is a new D. So let's call this D1, and this one is D2. So this is D1 here, and this is D2, all right? This D2. And because of D2, now you have another factor called K, all right? And K usually assumed to be approximately 4/3. Okay, so that's why you can see that this distance here is a bit further than the line of sight here. Okay, because it's 4/3, it's greater than 1. So D2 is a bit longer than D1. All right. Okay, so these are the formulas to compute the effective distance between a sender and a receiver, given the antenna height, right? The antenna have to be in meter. Don't forget this, have to be in meter. Okay, so this is the effective line of sight of a line of sight propagation. Okay. All right. Any question here? All right. Okay. Okay, so next, let me go to the next slide. Oh, okay. So talking about bending of the signal, right? Bending of the signal. So it's the same concept in Skywave here. All right. You can see here this line here. This line here, right? It's not really a. Oops, sorry. It's not really a reflection. It's not really a reflection. It's basically a refraction. That means this line here, if you draw it correctly, it has to be like a very, it should be something like this, you know, a very long line. So it, at some point it will reach the Earth, right? Because the distance is far, okay? But it's not really a reflection, it's a refraction, similar to what we've seen on this side here, okay? Similar to what we see here, okay? It's a refraction. It goes from the this upper layer of the atmosphere down back to the Earth based on refraction, not reflection, refraction, okay? Right. So next. Okay, so this is the summary of what we just talked before, basically a repetition. So don't forget that with this formula, the antenna height has to be in meter. The distance is in kilometer. All right, don't forget this because of this constant here. So this constant 3.57 assumes that the antenna height is in meter, the distance is kilometer, right? And this is in vacuum. So this D1 in vacuum, this D2 in on real Earth. Then you have K, and K is 4/3. Okay. Right. So next. Okay, and now if you have two antennas, right? So you must have an antenna to receive the signal because on Earth, there's nothing to receive the signal. If you have two antennas, then you have the height of one antenna is H1 and the other is H2. Then the distance, maximum distance between them is given by this formula, okay? Yes, this one is refraction, not reflection. That's a question from Adit. You mean this one here? Is that this diagram that you're talking about? Yes, okay. Like I said, it's not a reflection because this is air, right? It's not a hard surface. You cannot reflect something from the hard surface. Okay. This is refraction because every time a light or a wave go through a different medium, it will be bent, right? It will be bent. Now, this is the air, and the air has different densities at different heights. So basically, when you go from this point to this point, it's a different height. That means different density. So the light is bent a bit, right? But if you compare, let's say this point and this point here, you can see that the density of the air here is different from the density of the air here. So that's why it's bent a bit every time it goes through this distance, okay, at different height. Now remember, the height is here from to the earth, right? Different densities. So that's why the way of the light is bent. Okay, does that answer your question? It cannot reflect because there's no hard space surface here, yeah, to reflect anything. So this is refraction. Okay, right. So so there are many kind of impairments caused by different factors, right? To wireless transmission. So I think noise and thermal noise you have learned in 3213. Noise is interference from other signals. Thermal noise is caused by, at the receiver, caused by the movement of electrons in the resistors at a receiver. And when the electrons moves, it causes heat, right? And that heat adds to the noise of the signal, okay? So I'll go through, and attenuation and attenuation distortion. We talked about this before. Attenuation means the longer a signal moves, the weaker it's become, right? And not only the weaker it's become, it may be distorted as well, okay? Because it has to move through a long distance. So now we'll talk about free space loss, atmospheric absorption, and multipath, okay? All right, so attenuation, we've seen this before. Strength of the signal falls off with the distance between the sender and the receiver, okay? So what it means here is we must have good design for transmitters and receiver so that the signal maintain a level of sufficiently high signal than noise, okay? And the received signal must have sufficient strength so that the circuit of the receiver can interpret the signal. So this depends on the hardware itself and the distance. Don't forget the distance, because this is the formula, right? The longer the distance, the weaker the signal. And remember, this is important. Attenuation is greater at higher frequency, right? So we said about this before. Higher the frequency, the shorter the distance have to be, because the attenuation is much bigger at higher frequencies. Okay. Right. Now, free space path loss. So now I think we can do a quiz for 10 minutes, right? And then we take a 10 minutes break. And then we'll be back to complete this this lecture. I don't want you to wait any longer because you may be tired and you won't be able to do the quiz. Okay, so we give it this and then we come back later. 1 second.